Hello. Today we're gonna start discussing about the proof by induction in math. So why do we need to do or to understand about this topic? First of all, this topic is like a tool in math that we use to understand or to prove whether a formula do apply for a specific parameter in a specific question. For example, like the question that we have in here, right? So we have a series of sum, uh, 1, 2, 3. So we can see the pattern here. So the next one will be plus 4, and then plus 5, plus 6. So until plus n, and n is any positive integers, right? So as you may remember, integer is 1, 2, 3, 4, and positive means that we cannot use 0 or negative number. So the sum of this series, yeah, can be um, found by this formula, which is n bracket n plus 1 over 2. So how do we know whether this formula does apply for every n values? Maybe like n equals to 99 or n equals to 55, right? I mean, we can prove it. We can just plug in n equals to any number we want and see if we get the same value or not, but that will take time, right? So proof by induction means that we can actually prove this formula do apply for the for n is element of any positive integer, okay, without actually doing it the manual way. Yeah, so that's the idea for proof by induction. So what do we do first? So first thing first, before we start doing the proof by induction, we need to prove that this formula do apply for the initial value of n. So when we put n equals to 1 in here, so we're gonna end up with 1. That's the manual way, right? Because if the n equals to 1, so basically we just have the series consists of number 1, and 1 plus nothing is just equals to 1. Now, let's try to put n equals to 1 on the formula. So what do we have? So we're going to end up with 1 bracket 1 plus 1, and then divided by 2. So we're going to end up with 2 over 2, and that's also equals to 1. So actually the formula and the sequence are on the same value here, at least for when n equals to 1. Now, let's do one more. When we put n equals to 2 on the series, right? So what is the sum that we got? So it's just 1 plus 2, and 1 plus 3 is just equals to 3. 1 plus 2, and that's equals to 3. That's the manual way. Now, if we use the formula, we change the n to 2, so we're going to end up with 2 bracket 2 plus 1, and then divided by 2. So we can cross out the 2 in here. So we also get 2 plus 1, which is 3. So it still have the same value, right? Now, we already determined that at least for the first two terms, the formula is correct. Now we need to prove that this formula does apply for any positive integer. Yeah. So the first thing we need to do, we need to assume that the n can be any values of k, right? So why k? Well, it's just like a random variable, but the k here also have the same properties as n, which is what? Which is it has to be a positive integer. So now we're gonna change the formula into k. So we're gonna end up with k bracket k plus 1 and then over 2, right? And now so what is the next term after k, right? Because the n is element of positive integer, right? So like 1, 2, 3, 4, 5, and etc., right? The difference between the previous integer and the next one is plus 1 and plus 1 and plus 1 and plus 1. What does that mean? So it means that the next term after k is k plus 1, right? So now let's try to make n is equals to k plus 1, like this. So what do we have here? So the formula becomes, so we change every n on the original formula into k plus 1. We're going to end up with k plus 1 bracket, yeah, and then open bracket. So k plus 1 plus 1, k plus 1 plus 1, and then divided by 2. Okay, so now let's go back to the n equals to k here. So the n equals to k, right, is the sum of what? It's the sum of the series in number 1. Yeah, so we assume that it's the sum of the series on the number 1 and up until the value of k, right? So 1 plus 2 plus 3, right? And plus anything else until k, like that. So that will be k bracket k plus 1 over 2. Remember, this is just assumption. So we assume that the formula is true. Okay. Now, logically, if we change the n into k plus 1, right? So we get this formula, and this will be the sum of the series 1 plus 2 plus 3 plus blah, 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 plus k, and then plus the next term after k, which is k plus 1. That's the idea. Okay. So what we need to do now, we need to prove, yeah, that this formula is actually true. So how do we prove that? Well, first of all, our initial assumption is that when we add 1 until k, so the answer will be k bracket k plus 1 over 2. So take a look at this right here. This, up until here, sorry, it's the same thing with this one right here. So then we can change the 1 plus 2 plus 3 until k into k bracket k plus 1 over 2 because it's the same thing. So then we're going to end up with uh, k plus 1 bracket and then bracket k plus 1 is just k plus 2, make it simple, and then divide by 2. And that will be equals to this, which is k bracket k plus 1 over 2, k bracket k plus 1 over 2, and then what? Plus bracket k plus 1. So how do we get this bracket k plus 1? Well, it's from here. Okay, so now we just need to prove that the left side and the right side are equal. If they are equal, so that means that this formula do apply even for the next term of k. Yeah, so what we can do here, we can just try to make the right side into over 2, everything on the right side over 2. So we multiplied this bracket by 2, so we're gonna end up with k bracket k plus 1 plus 2 bracket k plus 1 and then divided by 2. Yeah. So now the left side and right side have over 2. We can just cross that out, right? So now let's try to do something to prove it here. Yeah. So what do we do? Well, is there anything that we can actually we can do something about this? They just expand the bracket, okay? So what do we have here? So we're gonna end up with k squared plus k times 2 is 2k, and 1 times k is k, so we get 3k and plus 2. And the right side here will be k times k, so we get k squared and plus k. This one will be plus 2k and then plus 1 again. So we're going to end up with k squared plus 3k. And this is plus 2, sorry, yeah, it's 2 times 1, it's 2. So it's plus 2. So as you can see here, the left side and the right side are equal in values. So what does that mean? So it means that we already proved by induction that for any value of k and the next term after k, the formula still remains true. Okay, and that's how we prove by induction for a series formula. Yeah. Now on to the next question. So the next question, we have something a bit different. The progression that we can see on this series is that the base of power is keep increasing by 1. So 1, 2, 3, blah, blah, until n squared. So then again, because the pattern is increasing by 1, so we can say that the n is basically any positive integer for the n bigger than 1. Well, of course, because n cannot be 0 in this case. So let's try to prove that the formula is correct first. So if we put n equals to 1 on the formula, on the sequence first, we only get 1 square, right? So 1 square is equals to 1. Now, if we use the formula, so what do we have? So we're going to end up with 1 bracket 1 plus 1 bracket 2 times 1 plus 1 and then divided by 6. Yeah. So we just try to add the bracket here. So 1 multiplied by 2, that's 2, right? And 2 times 1 plus 1, it's basically 3. So 2 times 3 over 6. Well, that still equals to 1. So that's correct. Okay. In a test though, you don't actually have to prove the n equals to 2. You don't need to do that. So as long as you already get the initial value of n, which is 1, yeah, then you can just leave it be this way. Now you can actually prove by induction. Okay. Now we're just gonna assume that if I add all this sequence until k, so 1 square plus 2 square plus 3 square, yeah, plus blah 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 until k, right? So our assumption is that the formula still remains true. Yeah. So then I'm gonna change the formula into k. So we get k bracket k plus 1 bracket 2k plus 1 and then divide it by 6. Okay. Now we need to change, we need to make sure that it's also true when the k is for the next term after k, which is k plus 1, right? So in that case, 1 square plus 2 square plus 3 square plus blah, 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 plus k, and then what's that? Plus, actually, it's k square. Sorry, it's k square, right? Because the one that is changed is only the base of the power here, so k square. And the next term will be bracket k plus 1 square, right? And the formula will be just change the n here to k plus 1. So we're going to end up with k plus 1, close bracket, open bracket, k plus 1, which is k plus 2, right? And then 2n plus 1, so 2 bracket k plus 1 plus 1 and then divided by 6. So we can just try to expand the bracket in here. So 2k plus 1 is basically 2k plus 2 plus 1, so plus 3, right? So we can change this thing into 2k plus 3 just to make it easy, like that. Okay. Now, just like what we did before, everything up until k squared, if we add them together, they'll be equals to this one right here. Yeah. So what we're gonna do, we're gonna try to use this formula and put it here. So we're gonna end up with k bracket k plus 1 bracket 2k plus 1 divided by 6 plus bracket k plus 1 square, and that'll be everything in here, right? So k plus 1 plus k plus 2, 2k plus 3 over 6. So same idea. We're gonna try to make everything into over 6 first. We just need to plug 6 in here. Yeah. So to because they will be multiplied by 6, right? And then we can just make the 6 gone because this one also have over 6 on the right side. So this one also gone. So all we need to know is proof that this thing, yeah, and this one is the same. So what is the fastest way to do it? You can just try to expand it one by one if you want to, okay? But it will take some time. So instead, what we're going to trying to do, we're going to try to factorize the left side here. Yeah. So as you can see, both k bracket k plus 1 to k plus 1 and the 6k plus 1 square have k plus 1. We can take that out, right? So we have k plus 1 bracket bracket k bracket 2k plus 1 plus 6 bracket k plus 1. Yeah. So that'll be equals to this one right here, right? So k plus 1 and then k plus 2 and then 2k plus 3. So because both have factor of k plus 1, we can cross out the k plus 1 because they are the same factors. Now we just need to expand the bracket, right? I'm going to do it here. So what do we have? So k times 2k is 2k squared plus k, right? 2k squared plus k. And this one will become plus 6k and then plus 6. That's for the left side. Yeah, for the left side. Now let's try to do the right side. Yeah, just this one. So k times 2k, that's 2k squared. And then k times 3 is 3k, and then plus 4k, so that'll be plus 7k, and then plus 6. And this one, k plus 6k, also 7k, right? So now the left side and right side is equal. So what does that mean? So it means that this formula does apply for any integer values, for any positive integer value. And that's how we do the second question. Now on to the last question. So as we can see here, we have a lot of we have a power again, an exponent question, but this time the one that changed is the exponent, not the base. So the formula given is 2 to the power of n plus 1 minus 2 for n is element of any positive integer and n is bigger than 1. So as usual, we have to prove first that this formula does apply for initial value of n. So when we put n equals to 1, then according to the manual way, so by series, it's just 2 plus 1, 2 to the power of 1. Yeah. So which is equals to 2. And if we use the formula, then we're going to end up with 2 to the power of 1 plus 1 and then minus 2, which is equals to 4 minus 2. So that's 2. So it's the same. Then we can proceed into the induction theory. So um, again, so 2 to the power of 1 plus 2 to the power of 2, yeah, until blah, 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 until 2 to the power of k can be represented by 2 to the power of k plus 1 minus 2, right? And then if I want to find out the sum of the term after k, which is k plus 1, right? So I'm going to end up with 2 to the power of 1 plus 2 to the power of 2 plus blah, 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 plus 2 to the power of k plus 2 to the power of k plus 1, right? So this is going to be equals to 2 to the power of n. Be careful, the n it become k plus 1 now. So we're going to end up with k plus 2, yeah? K plus 2, and then minus 2. So the same idea like what we did before. We're going to change the sum and up until the 2 to the power of k into 2 to the power of k plus 1 minus 2. So we're going to end up with 2 to the power of k plus 1 minus 2 plus 2 k plus 1 is equals to 2 to the power of k plus 2 minus 2. So we need to prove that these two numbers are equal on the left side and the right side. Okay, so how do you do that? Well, as you can see here on the left side, right, we have 2 to the power of k plus 1, and we also have 2 to the power of 2 to the power of k plus 1. So we have two of them. So that means we can add them together, right? Because it's the same base, same power. So we get 2 multiplied by 2 to the power of k plus 1 minus 2. That's on the left side. What about on the right side? Well, 2 to the power of k plus 2. So what can we do with this case? 2 to the power of k plus 2. If you remember a bit about exponent, right, we can change this thing into 2 to the power of k plus 1 plus 1, right? So why do I need to do that? Because I want to get 2 to the power of k plus 1. So plus 1 in an exponent or indices means that uh, it can be changed into 2 to the power of k plus 1 multiplied by 2, right? Because it's 2 to the power of 1 in here, yeah? Now, we're gonna apply this formula and just move the 2 in the front here. Then the right side will become 2 to the power of multiplied by 2 k plus 1 and minus 2. So as you can see here, the left side and the right side are equal. So we already proved by induction that the formula given are actually applied for any positive integer for this one. And that will be it for today's videos.